Okay, thanks for the introduction. Good morning, everyone. My name is Zhang. I'm going to present our research work BDA, a practical binary dependence analysis technique. This is a joint work from Purdue University, Renmin University of China, and the University of Virginia. First, let me introduce binary program dependence analysis. It aims at determining data dependence between instructions in binary executables. So let's look at an example. It initializes A as 0 and line 2, whose assembly code is a memory write, writing to the address pointed by RAX. Then it copies B or A to B at line 4. Corresponding assembly code is a memory read, reading from the address pointed by RCX. Because these two instructions are both operand on the same variable A, they are actually accessing the same memory locations. We call this two instruction dependent. Binary program dependence analysis tries to find all such kinds of instruction pairs. It has lots of applications, including call graph construct, malware analysis, binary writing, and more. Come to the example again. In assembly code, most memory addresses are represented by registers. Because of lacking symbol informations, it is difficult to identify if RAX and RCX are the same memory locations. So, a key challenge is to identify if multiple memory read and write instructions access the same memory locations. Several work has been developed into this research area. The state of art is value set analysis, which has been integrated into many binary analysis frameworks, including Anger and BAP. The high-level idea of VSA is to compute a set of possible values for each operand of an instruction. VSA uses a strided interval to over-approximate the set of values denoted by stride, lower bound, and upper bound. For example, interval 2 bracket 0, 8 bracket is equivalent to a set that contains 0, 2, 4, 8, 6, and 8. However, VSA do have difficulty scaling to complex and real-world programs. This is a program with one if-else statement and an assignment statement. Assuming during the analysis, the abstract value of RAX at the true branch is an interval from 0 to 2 with step 2, which actually represents 0 and 2. And at the fourth branch, the abstract value is an interval from 0 to 100 with stride 100. Note it is 0 and 100 actually. So at the control flow joint point line 5, the abstract value will be over-approximate to an interval from 0 to 100 with stripe 2. It is expensive and ineffective for the memory write based on such an over-approximated result. To see the evidence, we run the public implementation of VSA, including Anger and BAP, and observed that they failed on complex program of spec int. Anger failed on all the benchmarks, and we confirmed the result with authors, and BAP times out on most programs in 12 hours except MCF. ALTO is another technique. It is more efficient but more conservative. We will compare the BDA with this work in our evaluation part. So let's move on to the idea of this paper. Our work is based on two key observations. First, we observed that probabilistic guarantees are sufficient for many practical applications. So for example, in order to construct precise call graph, we need to derive indirect call target. To keep soundness, VSA will introduce lots of bogus call edges, making the final result not that useful. A more useful way is to find true call edges as more as possible and introduce less false positives. So our work will focus on probabilistic guarantee rather than full soundness. Another observation is that a dependence relation can be disclosed by many whole program paths. Intuitively, given a program with n statement, assume all branching statement has only 2 branches. So the number of dependence is O(n) squared, which is polynomial, and the number of paths is O2 to the power of n, which is exponential. Based on these two key observations, we developed the BDA, a sampling-based abstract interpretation technique for dependence analysis. So from now on, I will use source code to explain our idea, but our tool operates on striped binary executables. The first challenge is how to sample a path. An intuitive idea is to toss a fair coin at each predicate, which we call the naive sampling. Here we provide a counterexample to demonstrate the shortage. So this is a full function. First, it uses scanf to read string to the buffer. Then, checking functions validate the strings, and the function full will directly return if any check failed. After checking, a printf will be used to output the strings. The CFG is on the right. So we notice that there is a dependence from printf to scanf once the read path is executed. However, using the naive algorithm, the probability of sampling the read path is pretty low, which is only 1/64. In contrast, sampling the useless blue path has a more higher probabilities as 1/2, 32 times over the red path. As we can see, a naive sampling algorithm will be heavily biased by the path length. Note that there are 7 paths in the function full. An ideal case is that each path will be sampled using a uniform distribution with probability 1/7. I will explain how to achieve this later. Next, please let me introduce our tool, BDA. There are 3 phases in BDA's workflow. Phase 1 named path sampling, in which we aim at sample whole program paths under a uniform distribution. Phase 2 is per path abstract interpretation, which follow the sampled paths and compute the possible values for individual instructions. Phase 3 is the posterior analysis for dependence, which will mitigate the possible incomplete path coverage during sampling. In sampling step, BDA will take binary executables and its inter-procedural control flow graph as input and generate a number of whole program paths. Here is an inter-procedural control flows. The source code on the left shows 3 functions. The function main calls function full and function g. The function full calls function g's. Different functions are in different colors, and every node in the graph denotes a basic blocks in the code. The index of basic blocks are their starting line numbers. So for example, the BB14 denotes the basic blocks starting from the line 14. Different kinds of control flows are denoted by different kinds of lines. For easy understanding, we first assume the ICFG has no loop and no recursion. We also assume that each colony must return to its corner. So basically, we want to toss a biased coin at predicate to sample each path uniformly. So considering the first predicate at the BB1, assuming there are m inter-procedure paths starting from BB4 to the exit, and n paths starting from BB5 to the exit. Intuitively, if the coin is biased by the number of whole program paths for each branch, for example, we have n over m plus n probability to choose BB5 at the first predicate. Then we can uniformly sample the whole program path. So the first step is to do path counting. In this step, we will compute a weight for each basic blocks. The weight will denote the number of inter-procedure paths from the block to the exit of its enclosing function. The path counting is performed in reverse topological orders, in which we first sort the core graph and the nodes inside the function. The result orders is shown in the red numbers, and the circular numbers denote the weight. Following reverse topological orders, function g is processed first, and we can see the BB18 is 1, and the weight of BB14 is 2, because there are 2 paths inside function g. Inside function full, the weight of BB12 equals to 1 because it is the return block of this function. And for BB10, its weight is calculated by all the weights of its successors. So that is BB12 plus BB11 equals to 2. Considering BB8, it is an invocation site from function full to function g. So its weight should be the product of the colony weight and the continuation weight. The correlate BB8 has 2 paths, and the continuation BB10 has 2 paths. So there are 4 paths inside function 4. Function mains nodes are weighted in the same way. Note that there are 2 inter-procedural paths from BB4 to the exit and 2 paths from BB5 to the exit. So the probability to take BB5 is 2/3. Let's look at 2 paths. The path 1 is shorter and the path 2 is longer. Under our path sampling, both of them have the same probability to be sampled, that is 1/6. So that our algorithm will sample the paths from uniform distributions. We also address several practical challenges. The major challenge is that the weight of each block is extremely large. Intuitively, there might be 2 to the power of n whole program paths, in which n denotes the number of predicates. It means that we have to handle the heavily biased distribution, like 1/10 to the power of 1000. Note that a simple division will introduce huge error over a smaller part. We developed a novel algorithm to handle this, to simulate the biased distribution. And we will also handle loop and recursion and multi-exit. Details can be found in our paper. After sampling in phase 2, we perform per path abstract interpretation over the sampled path. The abstract value is singleton value instead of intervals, so that we can avoid the over-approximation problem in VSA. It is to some extent similar to the concrete execution. The aim of phase 2 is to compute the possible values for individual instructions and connect definition information and use information about memory. So this is an example CFG. Assuming the red path is executed and the address of way is deadbeef. Because block B writes to deadbeef, it denotes as a diff relation, and block E read from deadbeef, it denotes a use relation. Moreover, during the sampling, a dependence from E to B is observed. However, only sampling is not enough. Phase 3 is posterior analysis. It is aiming at solving problems caused by incomplete path coverage. Due to the huge search space, we cannot sample all the paths. Hence, we will miss some dependence belonging to the uncovered paths. Considering the previous example, there are 4 paths in total. Assume BDA only sampled 2, the red one and the blue one. So only the dependence from E to B and the dependence from F to C can be found. However, because BDA does not sample the dark yellow path, which covered both C and E, the dependence from E to C will be missed. To solve this problem, BDA will first merge memory write information at each control flow joint point. From the red path, BDA will find that block B writes to deadbeef, and from the blue path, the block C writes to deadbeef. So in the joint point block D, BDA will merge the result and observe that both B and C write to deadbeef. After that, BDA will cross-check the memory read information to detect dependence. At block E, because it's read from deadbeef, BDA will detect the dependence from E to B and the dependence from E to C. Moreover, BDA offers probabilistic guarantees. The 2 formulas describe the guarantees of observing a dependence. Detailed discussion is in our paper. This is an example who first assign SRC8 as null value and then copy string from source to destination. Assuming the looping unrolling is 15, when sampled 5 times, the probability of finding the dependence from string copy to the naive one is greater than 96%. When sampled 50 times, the probability is almost 100%. It is a strong guarantee for finding a dependence in practice. We implemented BDA in Rust based on Radar 2. The system is available on the following URL. For evaluations, we conduct a set of experiments to evaluate BDA. Due to time limitation, Here we present two of them. The first one is the evaluation on standard benchmarks for program dependence. We compare the BDA with VSA and ALTO. Note that it is difficult to get the ground truth of program dependence, even with source code. Therefore, we use two methods to evaluate the result. First, we run program with input provided by spec and use observed dependence as reference. Any dependence detected by reference execution but not by the analysis tools is called a missing dependence. Any dependence detected by the tools but not by reference execution is called an extra dependence. We also implemented a static type checker. It will check if the source and the destination of a dependence have the same type. The checker is implemented as an LLVM path, which will propagate simple information to individual instructions, registers, and memory location. Any dependence whose source and the destination has different types are considered as a mistyped dependence, which is most likely to be a bogus dependence. The result shows that although author does not have any missing dependence, the number of reported dependencies is very large, and 65% of them are mistyped. Such a result is not that useful in practice. In comparison, BDA reports 1 million dependents, which is 48 times smaller than ALTO. Half of the reported dependents are mistyped, with a negligible missing rate, 0.90%. From there, we argued that BDA is more useful in practice. Note that BEP VSA only handle MCF in 12 hours. Even only for MCF, BDA reports 5 times less dependence than VSA with a smaller misread type. Then we evaluate BDA in two downstream analyses. The first one is to identify indirect control flow transfer target for spec program. In this experiment, we compare the BDA with reference execution and IDA, a widely used commercial disassembling tools. The column 224 is the result on inference indirect jump, and the column 527 is the result on inference indirect call. Observe that BDA performs as good as IDA for indirect jump and substantially outperforms IDA for indirect call. None of the observed target is missed by BDA. Another application is to disclose hidden malware behaviors. Usually, malware behaviors is defined by its system and library calls, together with parameter values. We can perform static constant propagation through dependence to identify the parameter values. We compare the BDA with Cuckoo, a state-of-art malware analysis tool. The result shows that BDA reports 3 times behaviors than Cuckoo with the help of its accurate data dependence. For example, there are 3 critical library functions that are found by our tool but not by Cuckoo. They are trying to steal users' password, return remote shell, and remove all the files on the disk. So for related work, our work is inspired by random abstract interpretation and path encoding. Due to time limitation, I skipped the detailed discussion. So in conclusion, we propose a practical binary dependence analysis BDA. It features a novel unbiased whole program path sampling algorithm and a per path abstract interpretation. Under certain assumptions, our technique has probability guarantees in finding a dependence. Our experiment shows that BDA has substantially improved the state of the art, such as value set analysis, and it also improved performance of downstream applications, including inference indirect control flow target and malware analysis. So it's the end of my presentation. Thank you for attendance, and I'm happy to take questions.
situations there might be a very large of infeasible paths. So what impact does that have on your analysis?
Actually, based on my understanding, you are asking about the infeasible path influence on our result and the evaluations. So from our evaluation about program dependence, we can say that it do have some false positives. Actually, these false positives are introduced by the infeasibility path. So actually, I think we are trying to do a trade-off between the forcibility path or the soundness and the efficiency. And like VSA, it will track all the paths and to maintain the full soundness. So it makes the over approximation programs to make the result not that useful. So here we do such a trade-off to try to avoid the over approximation problems. Yeah.
Okay, thank you. So we have time for more questions. Could the next speaker set up while we take them?